Hey, this is Elektrofreak with my very first video on electronics design. My goal with this channel is to teach people how to build simple circuits to solve various problems. Yeah, it's going to be simple initially, and then I'll move on to more advanced stuff. But let's dive right in. I'll be using Eagle. The reason I'm using Eagle is I'm already familiar with this. I've done schematic design and also PCB layouts using this software before. So for now, I'll be doing my videos with this software. Eventually, I'd want to move on to other things like one tool that I really want to try out is Circuit Maker by Alti. So as you can see, I have Eagle open. My project is called Headphone Switch. Now, what's the headphone switch? Let's have a look at the schematic. So basically, I wanted to make a little box and then have two audio inputs, 3.5mm stereo jack inputs as inputs, and then be able to switch between either of them, or switch them off completely. And then I listen to that through a headphone jack. So this is the Eagle schematic capture environment. Right now, this video is not going to be a tutorial about Eagle as such. I could definitely show you a few simple how-tos for Eagle in future videos. For now, I'm going to focus on this little circuit. It's a very simple, really simple problem that I want to solve, and it's a very simple solution as well. Of course, there are many ways of doing this. So here I have, but of course, I really want to keep it very simple in the beginning. I could add amplifier and so on later on, but let's focus on the basic design. So I have two input jacks here. Okay. And then I have a double pole, double throw switch. So I need to be able to switch, left and right channels. That's why I have, double pole, double throw switch. So when I have switch in positions 4 and 1, for example, then I have the left and right channels selected from jack 1, which is X1 in this case, in this representation. And if I have if I have to switch in the other position, which is 6 and 3, then I've selected audio left and right channels from X2 for the second input. Yeah. Then I have another switch. I can either switch it to the output or just switch it, leave it floating. Meaning if I have switch in this position 3 and 6, 2 connected to 3 and 5 connected to 6, then I have the left and right channels on the output. If not, if 2 is connected to 1 and 5 to 4, then I have nothing. So just simple on off switch comes after the channel selection. Of course, ground, you need the ground connection as well. It's your reference point in the circuit, and we've connected. Basically, we've just connected these two to common ground, and so the same here as well on the output. Of course, this might be a little bit of a controversial issue. I think there are come across some forum blog posts saying that you shouldn't do common ground connection, but who cares? I'm not going for really precise or really hi-fi audio or anything. A little bit of humming in the system is okay, as long as stuff doesn't get destroyed. And really, there isn't much to destroy in this case. It's a very simple implementation, as you can see here. So I'm going to leave it at this. I'm going to leave this design the way it is right now. And of course, the next step is to look at a board layout, because I want to make a printed circuit board out of this circuit. So I switch to board view and click this button, and I've already done the layout. I did this layout last night, and it's very simple as it can be actually. Basically, I have, like, you see in the schematic, I have these two input jacks here, and then I have switch to select between the two. Now you can see I've tried to do most of the trace routing on the top layer. Now you can see this is a 2-layer board. How do you see that? The red is top layer, yeah, and blue is bottom layer. So it has 2 copper layers on this board, which we can use. So I try to do as much of the circuit routing on the top layer, but of course there are always exceptions. You can't do everything perfectly, yeah. So only exception to this was this trace here, which I had to route underneath, basically on the bottom layer. So otherwise, if I try routing it on the top layer, then it will overlap with this other signal from the second input jack, and then that can cause problem, obviously. So the solution is to do it under this chip. So yeah, basically I have these two connected here, yeah. Jack 1, jack 2, and then the middle is the output, the selected output. It will be either jack 1 or 2 depending on the position of the switch, which I've already explained. This is a push button or push button type double pull, double throw switch, so position 1 and 2 and so on. Then I have this output going to the switch here, the on-off switch. You can see these two go to the output, and this one is just left floating, really. So that's really about it. And then of course then I have then we need to connect ground somehow. The easiest way to do that is to define a ground plane. What you do is you draw a polygon, you draw a rectangle in this case around your circuit, and then you have to assign the name of this polygon to, oops, I'm doing that basically yeah. So you can see that I've named this G and D, which is the ground connection. Okay, so then what happened with that was all the ground connections on this board got highlighted. You can see ground of X1, ground of X2, and ground of X3 are all the same, and they're all going to be connected to this ground plane. Now, how do you actually get the ground plane? How do you fill this copper, so to say? You would have to click just click Ratsness, and then it creates this ground plane underneath, and of course spacing between this trace and the rest of the ground plane, as I already explained, this is the other channel, either channel left or channel right of X1, and that's it really. So you have this. Of course we can always optimize, make this smaller, make this more compact, move all the components together, but this is just to show you how you go from identifying a simple problem, creating a very simple solution for that, and then doing a final circuit implementation. Of course this is still not completed because I need to figure out mechanical stuff like I said, spacing between components and so on. Probably I'll have to move these closer inboard, and this one probably a little bit further away, and I'll move switches together and so on. And then of course I have to provide holes, mounting holes for the PCB, or I might just leave it as a bare board, without any box, because it essentially it does work the way it is. It doesn't necessarily have to be enclosed, but of course enclosing it is always a nicer solution, protects it from dust and water and so on. But yeah, but there's also the option to make 3D models out of this, but I haven't really explored that yet in Eagle. Probably that would be something of a topic for the next video, for example, or I might even do a new circuit the next time when I'm going to 3D modeling as well. Well, that's about it for now. Yeah, okay. Before we call it a day on this video, I'd also like to show you a very important thing that you should do before um, before signing off on your design, so to say, is to do the electrical rule check. So to see if the schematic and board are consistent. If there's unconnected traces here and there, that will show up as an electrical rule violation, meaning you have something laid out in the schematic, but they don't correspond on the actual board layout. So then you'll have to fix that by disconnecting and so on. Then a really important step is also, the design rule check. The first time I did a PCB layout, I had a shit ton of errors, huge bunch of errors, because I'd forgotten to do a design rule check. This might look really good, visually, but then who knows? So you do a design rule check. There's a whole bunch of rules that have to be followed while when designing a PCB. For example, clearance between traces, trace width, and so on. All of it is explained here. I'm sure there's more documentation online as well. I could link this in the description. Then sizes, drill hole sizes, and so on, shapes, supply, thermal isolation, solder mask, and you can also add stop masks. So if you don't want solder mask on a certain part of your PCB, you can also mention that. But this is of course a very basic standard setting. So I'll just go with the default rules. Of course, you're always free to change this depending on your design. But all that happens when you're a bit more experienced with designing PCBs. Yeah, I'll admit I'm not the most experienced PCB designer out there. It's a really vast field to dive into. But I try. I do my thing. So let's just do it again. Yeah. Just do check this time. So check, there are no errors. So possible errors, design rule errors would be, for example, if this trace was really close to this pad or this other signal, for example, then what would happen, or what could happen, is this would overlap with this pad here, and then obviously that causes issues during manufacturing, and that screws up your actual design as well. Things like that, and probably even spacing between traces is also one of the things that will be checked during a design rule check. And then those things, spacing between traces becomes really important when you're doing really high voltage designs. And you have to follow minimum space, clearance requirements. Sometimes you even have to do physical gaps in the PCB just to ensure that you have enough breakdown protection between two high voltage traces. But of course we're not doing high voltage at this point, so that doesn't really matter at this stage. But yeah, just so you know, just so you know this for future designs, in case I get into such designs. But yeah, anyway, I hope you understood whatever I hope you understood the stuff that I just presented regarding the schematic design and board layout. And enjoy the video. Give me a thumbs up, subscribe if you like, share, and all that social media jazz. This is Elektrofreak. See you next time.